All right, so this is going to be for Chem 1151, sections 6.1 through 6.4. So in this chapter, we're going to talk about energy. And just as a reminder, maybe from a physical science class, energy is the capacity to do work. We have two basic types of energy: potential energy, which is stored energy, and kinetic energy is the energy of motion. And the law of conservation of energy tells us that we cannot create or destroy energy. We can only change form. So we can take potential energy and turn it into kinetic and back and forth. Chemical bonds are a form of potential energy. And so we store energy in chemical bonds. To break a chemical bond, you have to put energy in, and to make a chemical bond, you get energy out. A compound with lower potential energy is more stable, just like if I were to hold up a rock. If it's on the ground, it's more stable. If it's high up, it's more unstable. So it has lower potential energy, is more stable. Reactions that form products having lower potential energy are favored. So in chemical reactions, a lot of the times, the reason, if you ask a question like, why does this reaction happen? A lot of the times it is because the products are lower potential energy, and so it becomes more stable. The units of energy, we're going to be using calories and joules. A calorie, lowercase c-a-l, is the amount of energy needed to raise one temperature of water, or sorry, raise the temperature of 1 gram of water by 1 degree Celsius. A joule is another unit of energy. Here's a conversion between them. You may see this in a homework. You don't have to memorize these conversions, but if you are given a conversion, you can use it. Using dimensional analysis if you want. Usually we talk about larger amounts of energies, and so we'll talk about kilojoules or kilocalories. One thing I want to note, a kilocalorie is also sometimes written as a big C, a capital C calorie. And that's what we actually see when you look at nutritional facts in the United States. You will see big C calorie when you may look at a similar product from a different country. You may see kilocalorie there as well, and that's the same thing. So it's 4,000 joules, not just 4 joules for a kilocalorie or a big C calorie. So when we talk about energy changes and reactions, you have to first break a bond. So to take a bond that's formed, we form bonds we can be more stable, right? So if we're going to break up something that's stable, we have to put energy in. And so we put in a certain amount of energy to break a bond, and there's a certain amount of energy associated per mole of that substance. And then when we form a bond, it's always going to release energy because it's becoming a more stable thing, because now everybody has that octet, right? So we've used all of these things that we're learning, and now we can start to explain why chemical reactions happen, why bonds are being formed. And it is always to make something that is more stable for the most part. So we can actually calculate how much energy it would take to make or break a bond. We call this the bond dissociation energy. We use this delta H, is called the enthalpy change. So delta, this little triangle, means change. And H stands for enthalpy. And enthalpy is a measure of thermal energy or heat energy. Heat is actually a change in thermal energy or change in heat energy. But I'll say heat energy just here for us, because I don't want you to get too bogged down in the terminology here. And I think that's something that is easy to relate to. Energy is absorbed. The reaction, we call it endothermic. Think about endo like enter. So heat is entering. Enters the reaction. And that change in energy is positive because it's increasing in the amount of energy. You're putting energy in, so it's going to have more energy. When energy is released, we call it exothermic. Think exo as heat exits. And so energy is lost, the change in energy is negative. So to break the bond, it would be positive or endothermic. We have to put energy in, enter energy. If we were making the bond, it would be negative. It would be exo, because to make a bond, we would get energy out or energy would exit. And so you can look at and think about chemical reactions in terms of bonds broken and bonds made. And again, positive values are endothermic. So breaking a bond, put energy in to break a bond apart, endothermic, positive value. Make a bond, energy out, negative value. And this is called the bond dissociation energy. And then when we're talking about breaking a bond, it's always give one electron to this side and give one electron to that side. So it's taking those two electrons from the bond and putting them back evenly on those atoms. So the stronger the bond, the higher the bond dissociation energy. And I like to think about it like this. The stronger the bond, the more energy it takes to separate them, right? So if the bond is stronger, it takes more energy to separate. And comparing bonds, they usually decrease going down the column. This is because iodine is really big. And because iodine is a really big molecule, that H kind of hanging off the end is pretty weak. But the fluorine is really small. And so when you have two things that are really small, it's a little bit harder to separate them because they get really close to each other. You can also think about polarity, right? What's the most polar bond here? Well, this is going to be the most polar bond because fluorine is the most electronegative out of all of these options. It has the highest electronegativity value. And so the more polar the bond and the smaller the atoms of the bond, the stronger the bond is going to be. You can also think about types of bonds. Single bonds are going to be less strong, double bonds would be stronger, and triple bonds would be the strongest. And so we can actually look at tables of different bond energies and really see trends in how these things are. So we can do calculations with this, but you have to remember, you have to figure out what bonds you're making and what bonds you're breaking, right? By looking at the Lewis structures. So relative strengths of the bonds are, if the delta H is negative, this means that, or the change in energy is negative, that means that heat was overall released, which means product bonds are stronger than reactant bonds. So products are more stable. If you release energy, if it's exothermic, that means your products were more stable than your reactants. And so it'll be harder to go in reverse. It'll be harder to break these bonds because they're going to be stronger. Think about if I went in reverse, it would be positive 213. And so it would take more energy to put in. We'll go in this direction, we actually get energy out. If we were to go in the reverse direction, we have to put energy in. So kind of here's the reverse. We got to put energy in. It's endothermic, then that means the reactants were way more stable, right? So you're not going to have reactants that are more stable going to products that are less stable unless you put effort in to make them do that. Otherwise, they're not going to do that. So it requires energy to do this. So for example, this is a combustion reaction. You know, combustion reactions are ones that give off lots of energy. This is like lighting a Bunsen burner. This is methane. Or like lighting up a gas stove, right? So that's going to give us lots of energy. This is photosynthesis. You know that photosynthesis requires constant energy, right? The photon of light has to go in constantly. When there's no sun, there's no photosynthesis. And so you have to put in energy constantly to get this reaction to go. So just a little bit of a summary here. Endothermic reactions, the delta H, the triangle H is positive. Heat is absorbed. You can think about heat being a reactant. So heat, it kind of is like a reactant. It's part of it, like baking a cake, right? That would be endothermic. Heat is the reactant. The bonds in the reactants are stronger. So we're having to force it to go to the product, even though the product is not as stable. Exothermic heat is released. You can think about the heat as a product. So like lighting a fire, right? The heat is coming off of it. It's a product. And so this means that the things we're forming, the bonds are stronger, or the things we're forming are more stable. So we use energy diagrams to represent this. Two things we have to think about with an energy diagram are the way that reactions occur. And so in order for a reaction to occur, two molecules have to hit each other. and they have to hit each other with enough energy to break the bonds. They also have to hit each other in the right orientation. So if you're trying to get a certain orientation, if these two touch each other, they're not really going to, they are going to do something, but if C hits A, it's not really going to do anything because we're looking for C to replace A, right, to hook up with B. So this would be like a single replacement reaction. And so an energy diagram is showing you how much energy do you really need to put in to get a reaction to go. So if imagine we start here with our reactants, you have to put in this much energy to break those bonds apart. The transition state is kind of like in between reactants and products. We don't really look at the chemical formulas or anything for that, but just know that it's kind of like halfway between reactants and products where you have maybe a bond, a partial bond between A, B, and then we have a partial bond between B, C. So it's kind of like this hybrid thing. It's kind of in between. So something with A and B and something with C, we're kind of breaking this one and forming this one at the same time. So it's like if you have removed, right, so this is your old place and this is your new place, you probably have some sort of transition state where you have stuff at your old place and you have stuff at your new place. You're kind of in both, kind of like in limbo for a moment, and then you transition fully to wherever new place you're moving. You have to put energy in to get to this point because we have to break these bonds. Now, once we get to this transition state and you've got open opportunity for each bond to occur, the more stable combination is going to happen. And so we are going to get energy out at that point. So it's like taking a bicycle and riding it up a hill. We got to put energy in. Once we get to the top of the hill, though, we can just let energy out. We all the way down that hill. The difference in our products and reactants energy, that's your enthalpy. And then this other thing we call the energy of activation or activation energy. And it's the difference between the reactant and the transition state. It's how much energy do you have to put in to get it started. Think about lighting a match. You don't just pull out a match and it lights in oxygen, even though there's oxygen in the air. You have to strike it, right? That's the activation energy to get it going. So this would be an exothermic reaction because your products are lower than your reactants. The higher your transition state, the more your activation energy, the more energy it takes to get that reaction to go, the slower the reaction is going to be. So the activation energy is the minimum amount of energy you have to put in. And so the reactants have to hit each other with that energy or they're not going to break those bonds. It's really the energy barrier. It tells us how fast the reaction is going to go. So low activation energy, easy to make that reaction get going, fast reaction. High activation energy, big hill to climb, slow reaction. So we've talked about this already, but if this is a lower energy barrier, it's probably going to be a faster reaction. And so you would have to actually compare two to each other to tell if it's going to be slow or fast. And then the difference in reactants and products is going to be your delta H. If it's a negative difference, and think about this math as products minus reactants. So you would actually look at the products energy, subtract the reactant energy, you would get a negative number if you did that, right? Because the products are lower than the reactants. And so this would be an exothermic reaction. Here's what an endothermic reaction would look like. We're going to have a big transition state, and then we're not going to get out as much energy as we put in. We're only going to get out a little bit of energy. And so if we think about our reactants, our products minus reactants, products are higher than reactants. So we would have a positive change in energy. That's endothermic. So both endothermic and exothermic require you to put energy in, but exothermic, you put in some, you get out a lot. It's like a good investment. Put in a little bit, we get back what we put in plus more. It's a good investment. With endothermic, it's not a good investment. I put in a lot and I didn't even get back what I put in. I didn't even break even. I lost money, right? So that's a bad investment. How can concentration and temperature affect reaction rate? You already know this stuff. Increasing the concentration of the reactants, it increases the number of collision and increases the reaction rate overall because there's just more collisions to be had. So imagine if I'm trying to get certain things to collide with each other, certain molecules to collide, if I put more in there, they're more likely to collide, right? So if you're thinking about if I put more cars on the road, we're more likely to have accidents because there's more cars on the road. Increasing the temperature. So this is like increasing the speed of traffic. If you let the cars on the road go faster, you're going to have more collisions probably. And you're also going to have more collisions at the right amount of kinetic energy to get the reaction going. So if we give energy to the reactants, they can hit that transition state energy a lot faster because they have more energy. So increasing the temperature, it increases the energy at which the collisions happen. So imagine this, if we had a bunch of cars in the road and we just increased the number of cars, but they were all moving very slow, you might not even have any collisions that did anything, right? But if you sped up the temperature and you increase the amount of energy that they all had, right, and maybe make them move faster, because temperature is a measurement of the kinetic energy, then you're going to have more collisions that do things. A catalyst is another way we can speed up a reaction. A catalyst basically is like a matchmaker. It puts the two reactants kind of at the right orientation so that the H2 or this reactant can really orient well with this reactant. It lowers the activation energy. It makes the transition state more stable. So basically what it's doing is it makes the transition state more stable, which means it lowers the transition state, because more stable means lower energy. So think about this graph. If I were to lower the transition state, my products and reactants don't actually change when I add a catalyst. The catalyst comes in, it helps my reaction, and it leaves. It doesn't change the reaction, but it does make the transition state a little bit lower energy. And so it makes the reaction go faster because now the top of the hill is not up here, it's right here. And it's just like a different route. So you go up this mountain this way, I find a way to go through a tunnel through the mountain and I can get to the other side faster, right? So that's kind of how a catalyst works. Like exactly what I was just saying. So the catalyst would be a lower, it starts the same reactants, the same products, but the hump, the hill is lower. And so of course it's going to be faster. Biological catalyst is an enzyme. The active site of an enzyme, it binds the reactant and then it undergoes a reaction. So for example, lactase converts lactose into glucose and galactose. If you don't have lactase, you can have intestinal issues from lactose, those people who are lactose intolerant. And so here's an example. So here's an enzyme. It's got a special shape that actually goes to the molecular shape of the lactose. And so we can see how it kind of fits in. So this is where what's important about the VSEPR stuff that we've talked about. The shape and the orientation of molecules actually makes a difference, because if the lactase enzyme didn't have this shape, or the lactose didn't have this shape, then it wouldn't fit and the reaction wouldn't work. The problem with people who are lactose intolerant is that we just don't produce a lot of lactase. All right, we will continue in the next video.